So welcome back. In this video we're going to be taking a look at bond character through the lens of electronegativity. And electronegativity, first and foremost, is the relative ability of an atom in a molecule to attract shared electrons towards itself. So the higher the electronegativity value is, the more able that atom will be to attract shared electrons towards itself. And electronegativity differences can be used to predict the bond character for a bond that forms between atoms. And I've got a chart here, and for quizzes and tests you'll get a chart. It's not something that you need to memorize. Probably the big four that you'd want to know are fluorine, oxygen, and then nitrogen and chlorine, because those are the highest electronegativity values on the periodic table. Fluorine is the most electronegative atom. Oxygen is the next most electronegative atom, and the nitrogen and chlorine are equally electronegative. And typically, the way that we're going to be calculating our bond character is through the use of electronegativity difference, so that delta in electronegativity. And if it's greater than or equal to 2.0, for this course, we're going to call that an ionic bond. And if it's between 2.0 and 0.4, we're going to call that a polar covalent bond. And if it's less than or equal to 0.4, we'll call that a covalent bond. Now, really, it's not quite as simple as that. We could also say that ionic bonds are easily identified as metal to non-metal bonds. That's a quick way to identify most ionic bonds. And when it comes to polar covalent and covalent bonds, that's typically going to be quick referenced as non-metal to non-metal bonds. So it can vary in terms of the way that the character works. Not all ionic bonds are necessarily going to be an electronegativity difference of greater than or equal to 2.0, but this gives us a nice reference point to use when we're trying to work out the identity. So if you have an electronegativity table, this is the ranges that I would ask you to work in. And so in the case of Na to Cl, we don't necessarily go first atom minus the second atom. If you are, then make sure that you're going absolute value for that difference. Otherwise, take the larger electronegativity value and subtract away the smaller electronegativity value. So in this case, we'd be looking at 3.0 minus 1.0, which equals 2.0, which makes an ionic bond. In the case of the S to F bond, we have S at 2.5 and F at 4.0. So in the case of fluorine, we've got 4.0, and in the case of sulfur, we've got 2.5, which makes a difference of 1.5, and that puts us clearly in the polar covalent bond range. At which point then, we could be identifying the partial positive end and the partial negative end. And so basically the symbol that I'm drawing is just this, almost like a coiled snake. And then when you put a plus there, it means that that is the atom in the bond that's going to have the shared electrons less of the time, and the partial negative is the atom in the bond that's going to have the electrons more of the time. And then in the case of the P to H, we have 2.1 minus 2.1, which equals 0. Even something like sulfur to hydrogen at 2.5 minus 2.1 equal to 0.4. Both of those would be considered covalent bonds, at which point we wouldn't need any partial positive or partial negative, as that's what that symbol stands for, partial, as opposed to in the case of Na plus and Cl, right, we would have a full plus and a full minus, because those are going to be full ions. The sodium will have transferred one electron over to the chloride atom, making a chloride ion. So that's pretty much the use of electronegativity values to determine bond character. Hope this helps, and good luck putting it to use for yourselves.